Okay, folks, it's going to be a quick one. Well, I'm going to move fast. That's not necessarily a quick topic. We're talking about scientific notation. It's just a way to work with large numbers and small numbers. So in this first one right here, we're talking about just large numbers. Cherish and Jayla did some research and found that there are approximately this many grains of sand on Earth. Cherish says that this is about 7 times 10 to the 15th grains of sand. Jayla says it's about 7 times 10 to the 18th. How did Cherish and Jayla each determine their estimates? We've got this 15 and this 18. Those are fairly big numbers. And if I'm looking at this number, I can kind of count right here, right? And so if I look and I see the zeros, I can count 3, 6, 9, 12, 15. So I'm assuming that that's where Cherish got hers. And then when we look at Jayla, we got that 15, and we got 3 more to get to that 7, right? So that's, I assume, how how Jayla got hers. So Cherish counted the zeros. Right? And then Jayla counted up to the 7. So whose estimate is more logical? I think that I'm going to say that Jayla's, because otherwise it would be 7,492 times 10 to the 15th. Be 7,492 times 10 to the 15th. Okay. So very small numbers. The size of a COVID virus is 0. All those zeros and a 1 meters wide. So let's see, I think it's like 6. Let's see, 1, 2, 3, 4, 5, 6. Yeah, 0.00000001 meters wide. That's what it is in scientific notation. The size of the bird flu is 0.00000008 meters wide. What is the size of the bird flu virus? Look, that's a misspelling. In scientific notation. So what we did here, right, for this, right? Oh, okay. Yeah, I don't know. We count how many zeros there are, right? So there's after the decimal, right? So I've got 6 zeros and then 1 more. So the idea is we took this decimal and moved it 1, 2, 3, 4, 5, 6, 7 times. That's where that -7 came from. Okay, so we're going to do the same thing. We're going to move this decimal, basically put it right here on the other side of the 8. So 1, 2, 3, 4, 5, 6, 7, 8. Right? So that becomes 8 times 10. Since it's a small number, it's going to be a negative exponent. Which virus is bigger? This is a -8. That's a -7. So this one is actually bigger. So COVID virus is bigger. Okay, so the way you kind of deal with these, right, you have counting number of zeros for large numbers and then small numbers, right? So what we do here is you go left here and your exponents increase, okay? So move your decimal left, right? So basically like starting here and going here. We moved it 18 to the left, okay? So move the decimal left, the exponent goes up. All right, so it goes from 10 to the power of 0 up to 10 to the power of 18, right? So this one, you move your decimal right and your exponent goes down. Let me start over. Move your decimal right, your exponent goes down. Who is it? Who is it? Who is it? Oh, can you return them later? Thank you. Okay, now we're going to do some operations with scientific notation. We're going to add, subtract, multiply, or divide. So how much greater is the mass of the Earth than that of the Moon? What does the exponent tell you about the magnitude of the number? So we have the mass of the Moon here at 7.35 times 10 to the... Golly, that's not a great copy. let's see here. 10 to the 22nd. Okay. So let me rewrite that because I'm just realizing that that's not a great copy. Times 10 to the 22nd for the moon, and then Earth is 5.97 times 10 to the 24th. Okay, now what we're going to be doing, so how much greater, this is going to be a subtraction problem, so we're going to take the mass of the Earth and subtract the mass of the moon. But when you are adding or subtracting scientific notation, you have to get the same exponent right here. So what I'm going to do is I'm going to, you can kind of move, we could move this down to 22, or we could move this up to 24. It really doesn't matter. It's going to get you the same thing. You just got to realize that if you're moving your decimal left, your exponent's going to go up, and if you're moving it right, your exponent's going to go down. So let's actually take this. We'll move this because we want our exponent to go up. So we're going to move our decimal left, right? So I'm going to take this. I'm going to move it here and here, right? Move it to this way. So this becomes 0.0735 times 10 to the 24th. Now what we can do is we can just kind of like line them up right here. 5.97 times 10 to the 24th minus 0.0735 times 10 to the 24th. Okay. So these are going to stay the same, and then the subtraction is going to be right here. So we're going to take that 5.97 minus 0.0735, and we end up with 5.8965. 8965 times 10 to the 24th. We'll round that actually to 5.9. Yeah, that's fine. Actually, no, that's fine. So what, times 10 to the 24th, not times 10 to the 4th. What does the exponent tell you about the magnitude of the number, right? So it's basically like, since we moved the decimal twice, a difference of 2 exponents means a difference of 100, right? Because it's 10 squared, right? So a difference of 2 exponents means a difference of 100 times. The planet Venus is on average 2.5 times 10 to the 7th kilometers from Earth, and then the planet Mars is on average 2.25 times 10 to the 8th kilometers from Earth. What is the average distance from Venus to Mars? You just got to realize that they're on opposite sides. So Venus right here, that's that 2.5 times 10 to the 7th, and then Mars, that's that 2.25 times 10 to the 8th. So we're just going to add, right? So we're going to take that distance from Earth to Mars here, and then the difference from Earth to Venus, we're going to add them up. So again, we got to move our decimal. Again, I can move this up to 8. I can move this down to 7. Since we moved this one up from 22 to 24, we'll change this one and we'll go down. So if our exponent is going down, we're moving decimals to the right. So this is just going to move to the right by 1, so it becomes 22.5 times 10 to the 7th, and then we're just going to subtract 2.5 times 10 to the 7th, because we've gotten the same as we shift our decimal to the right by 1, our decimal goes down, right? So moving your decimal to the right, your exponent goes down. Okay, so we're going to subtract here. This 10 times 10 to the power of 7 is going to stay the same. That's going to cancel, and then this is going to give us 20 times 10 to the 7th. However, this is when we get to, we should realize that we don't want scientific notation with 2 digits on the left of the decimal, so we're going to have to shift this decimal here to the left, and if we move the decimal to the left, our exponent goes up, so it becomes 2 times 10 to the 8th kilometers. All right. .25 times 10 to the 8th. Let me double check here. Let me see what I think I might have screwed something up here. 2.5 times 10 to the 7th, yeah. Moving it to the right, the exponent goes down. So it becomes, oh, we're adding. That's why I screwed up here. My bad. We're not subtracting, we're adding. So this becomes 24 point, no. That adds up to a whole, so we get 25. My bad. 25 times 10 to the 7th, and then we shift that decimal to the right, so it becomes 2.5 times 10 to the 8th kilometers, because it's an addition problem, so it should be greater. Ooh, I got that one. Okay. Now here, multiplying numbers with scientific notation, we've got 8.2 times 10 squared for our distance between our piers right here on our bridge. So we've got this Confederation Bridge. There are 43 segments right here. And so what we're going to do here is we're going to have this 8.2 times 10, what is it squared? Yeah, times 10 squared times 43, right? So we're just doing multiplication here. Now we can shift this decimal right here to make this 4.3 times 10 to the first, right? Because 10 to the first is 10. Gosh, can't see this, my bad. So 8.2 times 10 squared is the distance between them. And then there are 43 segments on it, and we're figuring out the distance on the bridge total. So we shift that over to make that 10 times 4.3 is 43. So that's how we get that. And so all we do here is we multiply the coefficients together. So 8.2 times 4.3, and then we take our powers of 10 and multiply those together. This becomes 10 to the power of 3, because we know we do with exponents. And then 8.2 times 4.3 gives us 35.26 times 10 to the third, but we don't want the decimal here. We want it one to the left, so it becomes 3.526 times 10, and as we move a decimal left, our exponent goes up, so that becomes 10 to the 4th kilometers. Okay. Same thing here. We're going to have 3 times 5, and then 10 to the 4th times 10 to the 3rd. So that's going to become 10 to the 7th, 15. But we shift that over, so it becomes 1.5 times 10 to the 8th. Okay, now when you divide, similar to multiplication, in 1968, Disneyland had this many visitors. 50 years later, in 2018, Disneyland had this many. The attendance in 2018 was how many times more than the attendance in 1968? So we're going to divide. So we're going to take that 1.3 times 10 to the 7th, and we're going to divide by 9.2 times 10 to the 6th. So it becomes 1.3 divided by 9.2, and then 10 to the 7th divided by 10 to the 6th. Okay, we know this is going to give us 10 to the power of 1, which is just 10, and then 1.3 divided by 9.2 gives us 0.14. So 0.14 times 10 to the first, we want to shift that over, so it becomes 1.4, and since we're shifting our decimal to the right, our exponent's going to go down. 1.4 times 10 to the power of 0, which is just 1. So this is 1.4 times more in 2018. Okay. Similar here, we got 2.4 divided by 6. Let's just put it on top of each other. And then 10.9 divided by 10 to the 8th. That's 10 to the power of 1. This is 0.4. Times that. We're going to shift to the right. This is going to go down. So it's 4 times 10 to the power of 0, which is 4 times 1, which is 4. Okay, real quick, last one. Distribute here, distribute here. So 5x plus 6x minus 12 equals negative 5x minus 60. 11x minus 12 equals negative 5x minus 60. We're going to add that 5x. To get 16x, we're going to add that 12 here to get negative 48. Then we're going to divide by 16 to get x is negative 3.